To start then, start the day. I want to begin by expressing my appreciation for your stalwart efforts and patience yesterday. I thought things went very well. I thought that you demonstrated admirable persistence and ability to deliver on those exercises we pursued together. And today we're going to be building atop those skills. We really laid a foundation yesterday that we're going to be building atop of. We're not going to be doing entirely new things, but rather we're going to be rehearsing those same skills and then tapping into some additional features. Yesterday we saw was particularly notable for having a wide variety of types of material featured. We started the day by doing a whirlwind look at a set of different models. And we particularly picked out models in each of the three major dynamic modeling traditions used in system science. To wit, agent-based modeling, where we saw a GIS type of model involving food-seeking behavior and impact of physical activity. A system dynamics model, which involved some service delivery representation, and then a discrete event model, which was also focused on the service delivery side and reflected a very articulated textured description of a trauma center. And I noted some of the features of each of these modeling traditions. Agent-based modeling, placing a big emphasis on agent-agent environment interactions. Each agent is a single individual. Those individuals may be people, as in the model we saw, but they might also be community organizations. They might be cities. They might be schools. And often the real central agents within an agent-based model are entities that make decisions or have dynamics of their own over time. And we capture them so that we can understand how their own evolution occurs and how it's tied in with the evolution of other agents and of the broader environment. So we situated these agents in a food environment, in a physical activity-related environment through parks, and we saw their interactions with those. And we saw how patterns at the high level, the aggregate level, could result from this interaction of agents at the low level. And when we looked at the system dynamics model, system dynamics as a tradition has a long history which spans very interestingly, and in a distinguished way for these three techniques. It spans both qualitative and quantitative components. It turns out that there's qualitative modeling, or what I'd call semi-quantitative modeling, in the system dynamics tradition that's very heavily used in a participatory fashion with groups. And I understand some of you in here have enjoyed the pleasure of interaction with my close colleague and collaborator, Peter Hoffman from Washington University at St. Louis. Peter is, as far as I'm concerned, far and away the foremost expert in pursuing participatory modeling in the health domain. System dynamics has a very long and established and, in fact, well explored tradition of using more qualitative methods as well as some quantitative methods with group model building a model jointly with others in a participatory fashion. But it also includes a very rich and, in fact, mathematically precise tradition of dynamic modeling. And yesterday what we saw was an aggregate, what I call an aggregate model. It depicted people in the population, in a hospital, for example, seeking care, using stocks, using these accumulations, and people flowed between those accumulations over time. System dynamics offers, in aggregate models like that, a sort of cross-sectional view of the population over time. It's not following each individual. You can't actually, in general, use it to say, tell me the number of times that this individual has been has come presented for care at the hospital. You couldn't readily do a breakdown of the population, how many people have presented for care 0 times, 1 time, 2 time in a histogram nicely. It's not at that level of resolution of following individuals, and it's not at the level of resolution of following individual events. Instead, it captures patterns within this population, and it has this sort of certain distance George Richardson talks about from the detailed events, and captures sort of overall patterns. But we could use it as a very powerful tool for understanding dynamics of a population over time. System dynamics is notable for having, because it taps into this very deep, rich mathematical tradition and applied maths of what's called ordinary differential equations, and using them. There's a set of tools we can use with system dynamics that can help us understand model behavior, help us understand how the system might behave under a wide variety of different parameters without having to run it exhaustively for all possible parameter settings. And it can be used with certain machine learning algorithms, particle filtering, for example, MCMC, in a way that is much more difficult for other types of dynamic modeling. System dynamics also gets applied at an individual level, and we saw that in some of our models, including the hybrid model and the agent-based model, in fact, the very first one. The third type of modeling is discrete event modeling. In discrete event modeling, or discrete event simulation, the term itself is a little bit confusing, because actually in those agent-based models, we were handling events that occurred at specific points in continuous time. And someone could say, well, that's discrete event modeling. And that's true, but there's actually a tradition of modeling called discrete event simulation. It's a proper name. It's not just a designation of how it works. It's an actual proper name for that field. And perhaps compared to the other two types of modeling, system dynamics and agent-based, which are fairly novel in the health space, not without exception, but fairly novel in terms of large-scale interest. Discrete event simulation has been applied for health service delivery for decades. Jeff talks about there being probably over 1,000 models of emergency departments in the literature that you'll find, and most of them are discrete event simulation models. They model, what's the characteristic of those sort of models? Well, they characterize the flow of some entity, in this case it was patients, through a set of processes that are resource constrained. The processes are well-defined workflows, and the process of a given agent, given entity going through that pathway is made possible by the availability of resources, by resource availability. So they won't be put under the X-ray until the X-ray machine is free. They won't actually be seen by the physician until the physician is done seeing other patients. That procedure room won't be opened up for them, that operating theater, unless there's a spot in its schedule. So it really focuses on, in a process-centric fashion, on the flow of these entities through the system with real attention to resources. And for good reason. Within this context, the interest is often, ladies and gentlemen, in understanding how resource availability or resource placement governs the throughput of the number of patients that can be treated per day, the waiting time of each patient, the latency, how long they have to spend in the entire facility, the resource utilization, what fraction of the time are those resources in use. So those are the three sorts of modeling. And then the final sort of modeling we looked at was a hybrid form, where all three types are combined. And AnyLogic makes this quite easy to do. And it's really exciting. And we'll talk about the implications of it. But one of the most profound is that as we learn in our modeling process, as we learn to what things the model is really sensitive, as our sense of priorities get informed by the model, we can change the boundary between what's captured using system dynamics, what's captured using agent-based modeling, what's captured using discrete event modeling. We can change those boundaries to offer us more detail on the things where the detail matters, and to aggregate up things and treat them in a more rough and ready way for areas where it doesn't seem like it's so critical. We can add resource-constrained processing using discrete event modeling for those cases where it seems really important to do so. So in short, this gets us to the next major topic we explored yesterday, to wit, motivations for system science and health. And I tried to situate that very briefly, in very brief remarks, in the context that we're grappling, ladies and gentlemen, with ever more complex health challenges. Whether it's our aging population, our shrinking globe, aspects of new emergent diseases coming from the animal-human interface, whether it's aspects associated with more nimble corporate actors or challenges associated with syndemics. We're confronting challenges that are more and more difficult. And when we're dealing with challenges, ladies and gentlemen, which exhibit factors such as reciprocal causality, where a person's health status influences their employability, and that, particularly in a country like the States, can deeply affect their health status. Inability to get health insurance can really lead to adverse health consequences. You have this reciprocal causality. One is tied up, entangled with the other. And we see that all across the world in health, where you have issues of nested context. My school as a child, I'm affected by my school, I'm affected by my neighborhood, I'm affected by the broader city. We have these aspects of nested context. We have long delays between those early life insults and their effects on chronic disease and risk factors down the road, potentially decades in the making effects. We see that there are profound influences associated with the networks in which we're situated in our geographic context. When we see nonlinearities associated with a person's response, the body's response, for example, to red meat consumption and carnitine. Very interesting work showing a real sort of nonlinear effect where if you're exposed to a certain amount or more, the risks just get much, much higher. When we have this sort of nonlinearity, and nonlinearity, the impact of interventions, we increasingly need to reason about not merely the pieces of the system in isolation. To really understand the behavior of the whole, to understand the effects of interventions, we need to understand systems effects. Just like if we're going to solve problems of traffic jams, we need to go beyond analysis in terms of individual cars, in terms of individual streets. We now need to start looking at the network of streets, how cars interact with each other. It's no longer just about the pieces, it's about the interaction between those pieces. Okay? So we talked about these sorts of systems, and we noted that system science uses dynamic modeling as a key tool to address these questions. And these models are distinguished by several factors. They depict sort of a theory of a system in a way that allows us to test more quickly the consistency of that theory with what's actually observed empirically. They help us learn more quickly, more deeply, and more robustly about external circumstances by allowing us to kind of think through the implications of theory together with the empirical evidence much more rigorously than we can do purely in our heads. So as Jeff talks about them, they're learning prostheses. And we saw that all of these models from any of those traditions is united by the fact they depict an initial state of the population. They posit how, based on the current state of the population, change will take place. Change can take place. Maybe it's hazard rates of progression or timeouts in agent-based modeling and state charts. Maybe it's flows and system dynamics. Maybe it's probability distributions considering how long you're in a given block, or resource requirements in discrete event modeling. They say, given the current state, how does what's going on over the next little bit of time depend on the current state? And then you can run the model forward. And that's what computers are good at, doing simple things many, many times. That's what's going on. Now, we then looked at this issue of statistical models and dynamic models. And I noted that a lot of the difference, not all the difference, these are two types of models that work hand in glove. They really are two wings of the same bird that allow us to fly when it comes to health systems insights. And they work together in very strong ways. System dynamics dynamic modeling as a general enterprise is forward-looking. It's one of its foremost goals is to be able to allow us to ask questions about counterfactuals. And to do so, it represents systems in a way that posit certain causal connections. Those causal connections that we posit aren't guaranteed to be correct. But rather than the model being a crystal ball, which either, in which we have to put faith and which may let us down, that model can help us spot if there is an inconsistency between what we posit and what the evidence suggests more quickly. And so these models, by capturing this posited causality, they can help us then ask what-if questions about situations we've never examined before. They could say, what if we were to have a food environment which has changed in this way? That fruits and vegetables are subsidized. Or what if we were to put in place a tax on sugar-sweetened beverages? Or what if we were to couple that so that the tax monies from the sugar-sweetened beverages are invested in infrastructure for physical activity? How would that ripple through to affect the health and weight of the population over time? We can start to ask about these counterfactual situations, some rather textured, some involving portfolios of interventions in effect at the same time within these models. By contrast, statistical models, by virtue of focusing on data that's been collected, by virtue of focusing on associations that have been observed, they can provide great insight into what's been going on, into some connections, particularly at the level of the pieces. But when it comes to counterfactuals, they run into challenges because they're positing associations that, or they identify associations that have been in place, but those associations might change in the context of counterfactuals. They can be extremely valuable for looking at the pieces and identifying associations at the level of specific risk factors and pathways of interest. But when it comes to projecting system behavior as a whole, when it's about the traffic jam, it's about the collective behavior, they often run into real challenges because those patterns at that level can change profoundly in the context of intervention or various other counterfactuals that might posit changes to the world either caused by our choices or caused by external circumstance. So dynamic models and statistical models work together, and it turns out one of the biggest uses of dynamic models is to incorporate, one of the biggest things we do with them is to incorporate findings from statistical analyses. That's a central way they work together. Another way is that the dynamic models can be used to test statistical models. And we'll actually see that a little bit probably in one of our examples tomorrow. Okay, we'll see how it could be used to sort of help evaluate a statistical model by virtue of feeding data from the simulation into a statistical model. Okay, in the afternoon yesterday, we covered several topics. One topic, in the first little component, we incorporated heterogeneity in models. So we built up a little model where we had heterogeneity in terms of three characteristics, to wit, age, sex, and income. And we saw that that for our model, we could very readily draw characteristics of a person in the population, the simulated population, from distributions. And those distributions needn't be independent. One distribution could depend on the other. And so we had kind of a conditional distribution for income, conditional on sex of a person, for example. And often in any logic where it's really convenient to define univariate distributions, even custom distributions which we choose that are univariate in character, we'll often use conditional decomposition in this way. We'll decompose a given problem into a set of conditional distributions and marginals rather than trying to deal with the joint. We can capture joint distributions, but they're not really easy to capture in any logic. They require more mechanism. So we took a look how we could represent heterogeneity, and I noted that that's no small matter. The fact that we can capture heterogeneity so readily is of significance because it can be very difficult to capture adequately in a Markov model or in an aggregate system dynamics model. For our agents, we simply needed to add a new parameter into the agent. Maybe it's income, maybe it's education level, and we could associate each person in the population with that characteristic, and then we could ask how does that characteristic affect their dynamics or their other characteristics. So very readily done. We then went on to talk about capturing dynamics of agents, and we did so capturing features of agent evolution using a construct known as a state chart. And I introduced this mechanism, there they are, this mechanism by which we could represent the features of agents in an agent-based model using an acronym. And the acronym was this acronym PARTES. And I noticed that Ross Hammond uses a quite similar acronym PARTE, which to describe characteristics of agents. The meaning of that acronym, or its decomposition into pieces, is given here. I talk about sometimes properties. I like to use the word parameters because it connotes more sort of static quantities. Each agent is associated with some parameters, some specification of the states in which they can be located, actions that change that state, rules under which those actions take place. The model is further associated with some time horizon, some time over which it takes place, characteristics. Is it discrete? It goes in hops of time, or is it continuous? By default in any logic, it's continuous. There are interventions that affect this state. One of the reasons I put interventions in there is because often thinking about them consciously, which interventions are important to you, shapes what you capture for the other pieces of the model. And then there's some environment in which this agent is located. Maybe it involves one or more types of networks. Maybe it's a GIS space. Maybe it's an indoor environment like we saw with the trauma center. So this PARTES is a very good way to sort of start thinking through what's associated with an agent and what's not. It helps you sort of focus your questions before you actually go to put it into any logic. It helps you think through what things you want to capture and what things are endogenous, what things are produced, such as being associated with changes in state, and what things are told to the agents but fixed, such as in parameters. And in that latter session, we introduced state charts which capture three of these. They capture states, they capture actions, and they capture rules. States are captured in state charts by those yellow states, yellow by default. You can color them as you see fit. Actions are captured in state charts traditionally through transitions between those states. Rules are associated with those transitions that indicate when do those transitions fire, under what cases do they fire, under what situations. And we explored two of them yesterday. One was what's called the timeout transition. It occurs after a certain time. An agent coming into a given state, after a certain time, they'll leave it on a transition. But we also saw that we could use a rate transition, in which case it's determined by a hazard rate, their evolution over time. So the rules specify the conditions under which these transitions take place. Now, one thing I didn't emphasize, but it's probably worth noting, it's a factoid of some significance for some people, is that those timeouts that we had, do you remember we had that first timeout with that agent? Remember they all blinked? at us? Yeah, do you remember that? Yeah. How could you forget? That blinking was associated with a fixed timeout. But in general, that timeout, we left it as 1 by default just for effect. But we could have drawn that timeout from a distribution. If you want to have their time in a state be shaped by a custom distribution, we could have, instead of having 1 in there, instead of having a fixed number like 1 or 10 or 5 years or time units, we could have instead put in a draw from a beta distribution, or have a draw from a truncated normal distribution. Truncated because we wouldn't want it to be negative. It's not meaningful to say we have a negative time in the state. Or we could draw from a log normal distribution, how long they spend in a state. So that timeout, it may seem awfully restrictive, but in fact it's quite the opposite. It allows you to draw from an arbitrary distribution how long they're going to spend in this state, which is very powerful. And it stands in contrast to like a stock in a system dynamics model, which taken in isolation is always exponentially distributed. It's with the exception of time varying rates, but in any case, the rate leaving it can't be dependent on how long an agent has been in it. So here we can have rates, we can have residence times you spend in a stock, be shaped according to an arbitrary distribution. So with that, we created finally a set in the culmination of yesterday and the culmination of your patience. We created interacting state charts. State charts where there's an evolution on the one hand of diabetes, the other hand of people's weight status, and one dependent on the other. And we could have had reciprocal causality. We could have the physical activity depend on the diabetes. So if someone's obese and diabetic, perhaps they're even less physically active because of concerns for hypoglycemic events or what have you. And so there's reciprocal causality. We could have readily captured that using the same basic mechanisms. And at the level of the plumbing of that system, we saw how we could introduce these things that were variables to sort of communicate that information. We saw how parameters in any logic could be placed in main, they could be placed in person, and they consistently serve two purposes. One, to encode assumptions, and one, to communicate those assumptions from the point of creation to where they're used. If the parameter was in main, its point of creation was the experiment, and so each experiment would tell the parameter what to assume for that parameter in main. So we'd have experiments that ran the model with different assumptions. And that was our primary mechanism for running different what-if scenarios. By contrast, if we had a parameter, which are denoted kind of like this, in any logic in person, where that person was created, for our examples yesterday, was always the population. So the population would specify the value of that parameter to use. Person, the class person, denoted personhood, the theory of personness, what it means to be a person. The particular assumptions about what values they had, their characteristics of the people, the particular data to be used, that was specified by the population of people. We might have population of Sydney and population of Melbourne, and they're a little bit different for the distribution of age, sex, and income, etc. Okay, so those are some features from yesterday. That was my retrospective. Before we go forward, any questions from that? Any questions about system science, about dynamic modeling, about complex systems, about the mechanisms of any logic? Any questions before we dive into some examples that build on what we did yesterday? Yes. Yes. Colin.
Yes.
Oh, yes. I'm trying to remember. I'm terrible with names. Apologies. Yes.
My background is working on interventions to prevent childhood obesity.
Yes.
And have a strong interest in systems because they allow a community in the planning phase to think about the complexity and the dynamic nature of the problem.
Right. Mm.
One of the things we've in this course for is to decide whether these modelling approaches are useful for evaluating the effectiveness of that type of intervention. So
right.
you've described them, and I can see the utility of them in terms of predicting what might happen should you do this,
right,
or should you do that. Potentially you could capture what actually happened in a community and use these models to describe,
yes,
and summarize and point to what it was that changed that made it
exactly.
differentially.
Yeah. So thank you very much, Colin, for that question. Did you want to say more, or should I comment on that?
So I guess that's a bit of a perspective I'm using is what's the utility of these in that space
right.
for evaluating
complex
interventions.
So I like that, and also I'm grateful to someone else, one or two other people who help highlight things that they'd be looking for. I'm going to try to weave that into some of the discussion. As it turns out, this is a topic which I'm going to try to hit some on Friday for the last day where we have some discussion actually concerning the nexus between these approaches and big data. Because I think that both of them provide a way of trying to delineate, trying to discern the predominant pathways by which interventions, for example, have had effect. And to be able to, very importantly, learn from the effects, say, of an intervention so that we can more effectively craft another generation of interventions that will be even more effective, to try to identify which pathways were nudged and which weren't. You think about an intervention, say, moving people from a low-income neighborhood to a mixed-income neighborhood. When you shift someone in that way, it has not just one effect, it has many effects, right? They're in a new food environment, and there may be grocery stores where previously there was a food desert and only convenience stores and very little in the way of fresh fruits and vegetables. But you've also placed them in a new environment from a physical activity standpoint and sedentary behavior, even separate standpoint. So there's less crime in this new area, and they're more willing to go out walking at many hours. There's more availability of recreational spaces in this area, perhaps better sidewalks so they can walk back and forth to school. There's easier availability of spaces to ball courts, etc. But there's also a changed social environment in this new neighborhood, right? So these kids who brought into new neighborhoods, they've been yanked out of their social networks back home, and now they're in a new social surrounds. And that's going to impact their behavior. They may be spending more time at home rather than out with friends at the local McDonald's. They may be focusing a little bit more because of that on other aspects of their life. And so when you look at results from moving to opportunity study in the States, there's many outcomes. And for teenage girls, you had lower obesity rates, you had higher high school graduation rates, and in general lower crime rates. But for teenage boys, you actually had marginal benefits on all those and slightly higher crime rates. And there's a lot of interest. Why did we see that? Which pathways were successfully nudged, and which ones did we run into trouble? What are the explanations for why we see these outcomes? And by implication, how can we do better? How can we design an intervention which learns from those outcomes and perhaps is more successful? And what are a big part of doing so is to identify what are the primary drivers for that reduction in obesity. Is it higher physical activity? Is it better food environment, lower sedentary behavior? Are the girls, spending more time at home and therefore less time at McDonald's? What's going on here, and what's going on with those rates among boys of higher crime involvement? To really tease out those pathways to effects, there's two great tools that I know of. One is modeling, and because in models we can represent those different pathways, ask what-if questions about them in the context of this intervention even before launching it, and then while it's running, compare what we're seeing from certain indicators with what we see in the model from comparable indicators captured in the model, totaling things up in the model, and that can help us posit what may be going on in latent areas that we can't directly observe, and help us potentially craft key measurement points or instruments that might tease out what's going on there along pathways that are ambiguous, whether we're seeing this effect or that effect. Well, if only we knew about this at this point in the process, we might be able to distinguish that. You test it out in the model and then deploy it in the community. So there's some real potential there. The other tool that I know about, and which complements that, is aspects of big data. And I'll be talking about some aspects of that. But we have invested very, very heavily in smartphone-based data collection of crowdsourced data and self-reporting on contextually triggered surveys and sensor data from things like accelerometers, GPS, et cetera. So between those and working together, I see there's a really great prospect for using models in this way to really tease out what's working, what's not, how can we change things for the better for measurement, how can we change things for the better for interventions, so that our next generation of interventions can even be better. And if we have community-shaped interventions, participatory interventions, which are often by nature adaptive, can we change this intervention in discussion with the community to improve it even while it's in effect? Because often community-focused interventions, participatory interventions, they blur a little bit that line between intervention planning on the one side being separate from intervention execution. They combine, and with reporting, being yet separate, they combine those fields in a way that might allow for flexibility. And I think models, one of the best uses of models is to be in that loop so that we can learn more quickly, we can communicate using models to the community what the implications of this are, and use that to drive sort of learning in the community level. So I'll see if I can address a little bit more about that and be a little bit more concrete about realizing that. And I would ask Jeff to help nudge me tonight to think about that for some of the exercises tomorrow, okay? So thank you very much. Any other comments and questions? Answering these sort of questions is one of the best things that I can do to help provide value, and I'm just so grateful when people bring needs up. So any other things people would like to talk about? Okay, what do you think? Do you think we should dive into some modeling? Okay, we're going to try to weave together learning from the models on the one hand with, big picture, seeing the forest, with the mechanism. Because many of you are here to learn the mechanisms, how we do things, but some are here to learn what and why we do things. And I'm going to try to go between them without exhausting any one of them. Okay? So, ladies and gentlemen, let's open that model we built yesterday. And I will stop this recording and we'll transition to a new recording. Okay?